Hi folks, this is Frank, and I'm going to talk you through some stuff in Materialize today, actually. This relates to a blog post that I wrote recently. I'll sort of throw it up over here. I'll put a link into the text down below. But it's about doing joins in Materialize and how that works in Materialize. And enough people have had questions about how this works and some of the sort of cool, interesting properties of joins and Materialize that I thought I would try to talk it through, in addition to having typed down a bunch of stuff. The blog post will be there, of course, so that you can totally go and, after the presentation here, and check out numbers, details, stuff like that back there. Complain if there are typos, things like that. I'm going to crib a little bit from the blog post as we go, so I've got it open over here. But the rough gist that we're going to talk through is the way in which many data flow systems, Materialize in the execution level is a data flow system, but the way in which many data flow systems do joins, streaming joins in that you might write in something like SQL, the way that they execute them in data flow, and in particular, how they keep track of their state. And that's going to be something that's different, a little bit different in Materialize than in other streaming data flow systems. And I'm going to try to call attention to that through a few progressively sort of, I think, cooler and cooler implementation techniques that we do. So I'm just going to zoom in this a little bit, actually. These are some numbers pulled out. That we'll do each of these things, pulled out of two different queries from TPC-H. This is a decision support benchmark from 1999 or so. So it's pretty old, but they're these sort of data warehousey looking queries where you join a bunch of stuff together and you do some aggregates over the top of it and distill down the results. And what we're looking at here for each of these queries are the number of records that Materialize will need to maintain. And, probably in some cases, most data flow systems will be at the top level here, need to maintain. So, you turn the system on, you feed in a certain amount of data. This is scale factor 1 TPC-H data. It's not very big, but we're trying to do this interactively to sort of demonstrate some stuff here. And we'll move through a few different cool techniques. So sort of baseline implementation where you just turn everything on and say, I don't know, compute the join for me, which is totally the same thing to do if you just want to go and compute one of these joins. And we'll sort of develop this a little bit. We'll show how by introducing the concept of indexes that you might, of course, be familiar with from a relational database, introducing them to a streaming system, we can start to cut down on the number of records that we need to maintain for each of these queries. And as we introduce more indexes, we introduce secondary indexes, which are indexes not on primary keys for a relation. The number of records drops dramatically, and I'll try to explain why. And then finally, there's a technique that turns on when we have basically all indexes available, which we call delta queries for lack of a better name. But this is an execution strategy that I'll talk through this as well, where you can totally see, for query 8, the number of records you have to maintain has dropped to 6. Those basically, there's 6 results in the aggregate at the end of the computation, and we need to maintain no additional state, which is a fairly nice thing. The catch here, of course, right, is that these numbers are all the incremental number of records. So how many records does query 8 need to maintain in addition to the indexes that we're maintaining? So if we think of the indexes as a fixed cost, they do cost for sure. But if we think of them as a fixed cost that doesn't change as we add or remove queries, then the incremental cost of each of the queries that we're adding in is, potentially really quite small. So we'll walk through those. I'm just going to spend a moment or two just to get everyone on the same page here with, what's a join? You may be super familiar with this. That's totally fine. I just want to call out what our queries are going to look like, essentially. I've got a bunch of TPC-H queries next screen over, and they're going to have some idiomatic structure that's going to look roughly like this. So this is a join in SQL. It's a select statement, which says what columns do we want to pull out as our results. It's got a from clause, which says where are we going to get this data. And as soon as you see a from clause with multiple lines in it, multiple different sources of data, customer and location in this case, you're likely to have a join. We have two different data sets, and we're going to, what SQL says this should be is the Cartesian product of these two. Now, the Cartesian product's a lot of data, so you throw in something like a where constraint that correlates two of the columns here, the zip code, let's say, for the customer and the location. And SQL-based systems are smart enough to say, whoa, this, I should do more than just form the full cross product and apply a filter. I should go and implement something like an equijoin or what have you. So this is something that will produce a whole bunch of customers and names, customer names, and also for each of them the state that their zip code is located in. I'm sort of imagining that location has zip as a primary key and a state identified for each zip code. All right, so that's what a join looks like. Things get more complicated. One of the examples we're going to run with for a while has 3 different inputs that are going to get joined together simultaneously, and the number goes up. Like we've got some examples in TPC-H that are like, I would say like 8-way or maybe 6 or 7. We'll see as we go because we've got them all over there. So, so this is great. Let's dive down, and this is the picture that I drew. I don't want to redraw this because it's a pain, but picture that I drew, and what it's drawing is a standard data flow approach to doing joins. So if you think of data flow systems as communicating about streams of data, so maybe a stream of data about the customer relation, the records that are added to it, for example, and a stream about the location data, things that are added to it. The join operator that most data flow systems would implement says, great, I'd like to have access to both of those streams, please. I'm this join operator over here on the right-hand side. And don't worry, I'll figure out what to produce as my output. Though in the course of doing that, the join operator is almost certainly going to maintain a lot of private state. Essentially, it needs to keep track of the accumulated history of customer and the accumulated history of location. Because if there's a new entry in customer, for example, we have to be able to look something up in location and say, well, you showed up, you've got a zip code, I need to find your state. Or if for some weird reason, a new zip code is added into a location, we might need to, or modified or something like that. We need to track down the customers who previously either matched to the old value or didn't match at all, what have you. So the join is going to maintain that state privately in a lot of data flow systems out there. And totally fine, like this is a sane way to try to design systems because join sort of has control over its own destiny at this point, and it can totally choose the implementation strategy that's best for it. So there's some totally sane ways to do this in data flow systems. It's not how differential data flow and Materialize are going to work, though. Let me sort of draw a little picture about that. So joins and Materialize have a slightly different implementation strategy. It's got similar structure, right? So customer and locations are streams that come in. And there's this operator. I've called it join core just to make it clear that it wasn't the same join operator as up above. It's an operator. Join core is actually the name in differential data flow for this operator. But what's going to happen is instead of join core maintaining its own private state, it is going to take both from customer and location the streams of changes coming in. But after they've passed through this slightly interesting operator called arrange. Arrange is a logical no-op. It doesn't change the meaning of the data. The same changes that come in go out the other side, but they're represented differently. In particular, they get, it's called arranged, basically. You can think of this as indexing, if you'd like. They get shuffled around between all the different workers and put into batches that are indexed by some key. And the state that the arrange operator maintains is essentially the same state that join would have maintained. You can think about it, if the data come in, they have key and value, then the arrange operator is going to maintain a map from key to all of the values associated with it. In particular, to all of the history of all of the values associated with each of the keys, which allows operators like join to grab a hold of that and look through all of the history for each of the keys and each of the values and reconstruct the state at a particular point in time in the past And basically it can function as a correct join implementation now by instead of maintaining private state, using this more public state that exists, which is nice. It's nice for a few reasons. It does make things a little bit more complicated. That's totally fair. The join core operator itself is of course much simpler, but the whole setup is a bit more complicated. But the nice thing that does happen is that other operators in principle can use the same state. Not only that, we could potentially prepare the state ahead of time, right? So if customer just happens to be a data set that we're sitting on, we could arrange it and say, great, we've got this arranged. And now any number of queries can show up and say, I'd like to join customer and maybe some other relation, billing info or something. And rather than reread all the customer data and start working on that, we can actually just wire up a new data flow that borrows exactly the same in-memory state data asset and needs to do no work for that customer data. Of course, unless the join operator will need to grind through it looking for matches in the other relation, but it does not need to get new copies of all the data or build indexes of them. So this is sort of handy. This means that, in just this one picture, we're keeping the same amount of state as before, but it means that there's a reduced cost to running differential data flow computations and materialize computations when we know that we're going to be able to reuse various indexes. That's useful both if you want to pose a lot of queries, but also as we go along, there are some join plans that reuse these arrangements even just within the single join that allows them to use substantially less memory. That number 6 that we saw before was due to clever reuse of arrangements, and hopefully we'll get to that. All right. What we're seeing down here is essentially what I was just talking you through, and I don't want to read you essentially the whole blog post. Probably that's not super fun. We're going to run some computation. That'll be more fun. This is just showing you that you could totally, if we already had an arrangement for location, just slot that in instead. Like we don't need to actually feed the stream of location changes into anything called arrange in a data flow. If it already exists somewhere else, we can just link that up, and the computation runs as if we had given it the whole stream of updates and arranged them ourselves. Cool. All right. So this is going to have some consequences. Basically, the consequences, we'll talk through a few different levels of interestingness of the consequences. There's a particular query that we're going to use, which is Tpch Query 3. I've written it down here. Actually, this is sort of much more nicely formatted than on my other screen. So let's take a peek here. This is Tpch Query 3. And it's not, don't worry too much about what's going on here. Like structurally, if you scan down to this from clause, there's 3 input relations: customer, orders, and line item, which is sort of like events. Is one way to think about it. Things going on with shipping of pieces of orders. There's a bunch of constraints, and you can see that some of the constraints, there's like market segment and order and ship dates. But there are these 2 equality constraints relating the order key and the customer key. So customer key is a primary key for the customer relation, and relating L order key with O order key. O order key is a primary key for the orders relation. So one way to think about what we're doing is we're taking all of the line item events, joining them with orders on the order key. It's basically a lookup to find the order associated with a line item. And then we're going off from the order to the customer and restricting our attention down to just those line items and orders and customers, where the market segment is building and the ship dates and order dates are, essentially this is, things ordered before a certain point and shipped after that. And having pulled all this data out, sort of join, we're going to do some grouping, and we're trying to figure out some accumulation of prices up there by essentially by order, right? The order key up there is a primary key, so the order date and ship priority are functionally dependent on it. So we're really just trying to ask for each order out there, tell me about the sum of orders satisfying with any line item satisfying these constraints. Tell me about the the price minus any discount, looks like. The revenue, I suppose. Yeah, and that's the query. We're going to run this query a few different ways. And the different ways are going to give us different results in terms of essentially how much memory does it require. So I'm going to dive over there to my little high contrasty screen. And I'm going to turn on a copy of Materialize. Materialize is running up here. I'm not giving it much real estate because we don't really want to see what it's doing. Also, there's some annoying errors. And I'm going to turn on in a second terminal a P-SQL connection. So this is now an interactive shell where I can see which views are installed in Materialize and interact with it. So for example, what I'm going to do first is create a source. Creating a source is a metadata action in Materialize. It just adds to our catalog. Where should I go and find some data if you ask me to use it? So I've got some line item source here. I'm just pointing it at a generated .tbl file. This is something produced by the TPC-H data generator, scale factor 1. It's not a lot of data, but again, we haven't actually even done anything with it yet. What we can do next is create a view. And what this view is going to be, in this case, it's really not that complicated. It's going to take the source, which is just 17 CSV columns. It's just text everywhere. And it's going to essentially give instructions about what the types are and what the name should be and stuff like that. So whereas instead of column 1 through column 16 as text, we're going to pull out various things as integers, decimals, dates, stuff like that. And give that a new name. That's also just a metadata action. So creating a view doesn't cause any computation to happen. It just lines up, sort of tees up some computation if you like. So if we were to go and use this, if we did select count star from or something like that, we might actually cause any of this computation to happen. We're not going to do that though. What we are going to do, just quickly, is grab each of the other sources of data. I've got some corresponding files there and some corresponding views that parse each of these things. And pull them down, and just toss them into Materialize. So now if we do, for example, show sources, we get a bunch of sources. If we do show views, we get a bunch of views. And in principle, we could think about starting to drag. Now, we haven't done any work yet in Materialize other than changing the catalog to refer to these sorts of things. So before we do anything, well, actually, sorry, take that back. Let's go find query 3. So this is going to be, here's query 3. Query 3 we can install as a materialized view, and creating a materialized view, this materialized keyword here is super important. Creating a materialized view will actually prompt computation to happen. And if we sort of check things out, we can, query 3 will start to be populated at this point. And it should keep going up a little bit as we read more and more data in. This is, should be quite clear. This is announcing that it depends on each of customer, orders, and line item. But as we turn on this query, we're discovering for the first time what are actually in each of those relations. So we're now running over, opening up some files, starting to parse things out of them. And we should, that looks like, we should eventually reach the right number of aggregate values in there, which this happens to be. And if we were to go and append some more lines into that file, we would totally potentially see some new aggregates. They might just stay this same number of aggregates, but have the values change. So this is one of the ways to go and run a join and materialize. This is the one that corresponds to this sort of first example where this data flow creates sort of private indexed copies of customer, orders, and line item because it's got to, right? It doesn't have much of a choice. There's nothing else it can rely on. So what we can do now, since this is up and running, is start to ask some questions about it. Like we could totally look at the data if we wanted to. I don't really want to do that. It's totally fine. We could. But we can take this query here, which before we do that, I'm sorry, bouncing around a little bit. Just show off one other thing that we can do first, which is explain plan for. So any query out there, particularly the query that we just installed as a materialized view, we could look at the plan for it. And probably, to be honest, we should have done this before we installed it as a materialized view, because the plan could have been terrible. It could have told us some pretty horrible things. I'm going to grab a copy of this, actually, because we're going to make some changes that will cause the plans to be different. So I just want to steal a copy and keep it off to the side. What the plan is telling us is the first 3 steps are just saying, like, here's some names of things: customer, orders, line item, and it's pushed down some filters so that, like, at the moment of reading these things in, we should be able to filter out, anything that's null in various primary key fields. And there's some constraints, if you recall, on dates and market segments and stuff like that. So those all get pushed down. And the computation really isn't, like, structurally isn't that complicated at this point. There's a join that happens between these three inputs. And there's some, reading this is sort of a mess. I don't want you to try to do that. But there's some equality constraints that the join is going to impose that's going to give it its join structure. And we follow that with the reduction. And this is the reduction that uses as keys whatever it was, the order primary key, and then ship mode and stuff like that, and does the aggregation where we look at the revenue. So that's the optimized plan. That's not what the data flow looks like. The data flow is going to be more complicated than that. We can take a peek at the data flow, actually. That's got one of our memory visualizers up that we can go look at. We can look at the primary index for query 3. And it's kind of complicated, actually. I'll try to talk you through what each of these things are. The red data flow operators are the ones that are potentially stateful. And that's pretty exciting. Particularly these 4 of them that you can see on the screen right now are going to be the ones that are maintaining our input data, essentially. So these things like customer, line item, and orders. And their numbers will be relatively larger if you made the data bigger. Some stateful stuff down at the bottom, and you can sort of see these are holding things proportional to the number of outputs, the number of distinct keys in our reduction. Over here we have, this is something that's maintaining the errors that have been produced throughout the data flow computation. Fortunately, that's 0, but it could have been substantially more. And there's a bunch of guff up here that I hope you don't look at too hard. These are various operators related to, you can sort of see decoding CSVs and demultiplexing erroneous results and correct results and various bits of stuff like that. A lot of the data flow is related to what happens if someone produces an error somewhere along the computation. So if you tried to parse out some data that wasn't UTF-8 or something like that, we need to push that error cleanly along somewhere for you, because you could then go and retract your incorrectly formatted data, and we need to correct our computation as a result. Anyhow, fun stuff there. So that's roughly what our data flow looks like. You can see that there are these four stateful operators. You might wonder, why are there 4 stateful operators? There are only 3 inputs. And the answer to that is that we need to, you can sort of see the structure here. There's a join here and another join down there. We're going to be able to join 2 of the inputs together, so right off the bat. Probably, I'm going to guess these are line item and orders, because they're relatively large. But we don't have a ternary join operator. We just have binary joins. So the binary joins move along and need to then get, the output of the first 2 joined together needs to then be joined with whatever the third one is, and that join needs to have its input arranged, right? Its input needs to be kept indexed as well, so that changes that flow in for this third input here can immediately hit some index representation of data. So there's actually 4 places that are holding onto data with various numbers, stuff like that. And there's a query that we can use to pull this accumulated total out. That query is the one that I had thought that I was going to run without giving you all that exciting explanation. So if we fire off this query, now this query is going to pull out, we'll see what it looks like, and then I'll try to explain it. So this query is telling us, for each of various data flows that are registered in the system, there are a whole bunch of data flows. You could sort of see all of them here. Right, so these are all of the data flows that are active in the system. with various, we can check out their data flow graphs as well. Most of them are quite simple because they're just inputs. Telling us for each of the data flows, how many records is the data flow maintaining, right, across all of its operators, that sort of thing. And you can see that query 3 primary index, which is the name of the data flow that we had to build to house query 3. Yeah, it's got quite a lot of things, huh? There's some other slightly smaller internal things here. This is, for example, something describing a whole bunch of columns that we have in our system, stuff like that. Whatever. You can see that these are, this is chump change down here compared to all of the data that we're maintaining up here for query 3. But, it turns out that's roughly the right answer if we go and we look at that picture again. If you go and check it out, and I have, you can see that this number here. So there's about a little over 6 million records in line item, but we can throw away almost half of them because of the date constraint that's on them. So about half of the records make it down to this point and need to be indexed. It's a nice property of Materialize, right, that we got to wait until we saw those filter constraints and only materialize the data that we actually need to retain. It's pretty handy. But that checks out as the number that pass that constraint. If we look up at orders, this ends up being the right number, and all these things joined up and whatnot. These end up being the right totals. So, it's a number. It's bigger than you might like. It's if we look over at our chart, should be roughly this number. There's a little bit of variation because this is like physical records maintained on disk as opposed to logical records. But it's actually the same, I think. Yep. No, these are identical at the moment. That's good. All right. So, what can we do differently? Well, we didn't have to make this data flow computation all by its lonesome. So let's show views. We have query 3 here. I'm just going to drop query 3. This will, this will essentially delete the data flow, uninstall it, and those resources will be reclaimed. What I'm going to do instead now, though, is to say, hey, several of those things that we joined, you might recall that we had orders and customers involved. And each time we did a join there, we needed them indexed by their primary key. So if we happen to have indexes lying around, actually, I'm just going to take I should take all of them. I was going to try to be clever and just take the ones we needed, but let's just do all of them. So this is going to create a bunch of indexes. This is going to take a little bit of time. We are reading in data. Each index that we build says, go and make an arrangement for me. Go and do that arrange operator that you mentioned. There's no additional data flow yet, but just go and do the work of building index on each of these relations. And keep it up to date for me as the data change. Keep it ready for me in case I show up and ask a question that might benefit from it. So that's going on, and actually we don't need to wait for it. I don't think we can totally just go and we can ask some questions actually first. So let's do that explain plan thing, for example. So if we do an explain plan for our query, the plan probably looks pretty similar to you, though there's some important differences. Let's grab this and put it next to this plan. Apparently it's a bit wider, but the main thing actually is that both 0 and 1, which were customer and orders that had filters applied to them and stuff like that, no longer have filters applied to them for some mysterious reason. And I'll try to explain what that is. Although not evident from these descriptions here, we're actually going to be reusing the arrangement both for customer and for orders. And as a consequence, it doesn't make sense for us to try to filter. If we go and change the data by applying a filter to it, we would have to rearrange the data. Right? We're already sitting on an arrangement, and that's pretty sweet. So what we're going to do instead of applying the filters eagerly is those filters will move later on. Essentially, they're going to show up like that building constraint, for example. Used to be up here on customer, it's now going to be put as a filter after the join, and actually it'll get moved into the join in execution. But we're going to keep the data arranged. Oops, I'm not sure that actually helped. We're going to keep undo that. We're going to keep the data arranged as they were, and the reason is that this is going to allow us to benefit from prearranged data. Let's check out and see if we can actually see that now. So we're going to reload the active data flows here and go look for, some exciting things to see. We have various primary key indexes. There's probably 8 of them, I'm guessing. Line item customer. Okay, so each of these is a little data flow that's just, what does it look like to read in the data from CSV mumble, arrange the output. This is the number of records in line item, and any errors that might have resulted because technically we could have errored when we were generating the keys for each of these things. That's exciting. So we have a bunch more new indexes. They have records that they're sitting on now, and we could totally actually let's do that. We could totally, before materializing the view, go and look and see. These are the new number of records by data flow there. You can see that, we used to have 4 million or something like that. We now got even more, right? Line item had 6 million records in it, and we're sitting on an index of all the records in line item, as well as some of the smaller relations that are also indexed and at hand. Orders, for example, has 1.5 million records in it. And this is 1.5 million records we're not going to need to reprocess when we materialize query 3 the next time, because we needed orders exactly by this primary key. So let's steal this view again. Drop that in there. And this will take a little while to get going, but probably not too long, to be totally honest. Things are a lot faster once the data are already in memory instead of off on files. So we're going to reload our list of active data flows. We'll go down there and we'll see down at the very bottom there's a new data flow for us to look at. Pretty exciting. And it is, so data flows, Materialize have, in timely data flow, but also Materialize, have potentially nested scopes. And the top level, there's a region, all of the inputs that are coming in, and a region. Within the region, we have a lot less guff, if you remember all the guff related to inputs. But we have now, you can sort of see it here, a bunch of operators and some just sort of surprisingly absent red circles, right? So we have a join operator here, and coming in, you might recall, hopefully it's true, the number of records that passed from line item that passed that filter was this number. It's being joined with orders, though there is no red orders operator over here. It's actually, this is representing the arrangement that corresponds to orders, and there's no state that's costing for that anymore. The state is outside the data flow. I mean, it still exists, of course, but it's outside the data flow. Same thing with customers. Customers here, going into this join operator, there's, we had that arrangement that we needed to maintain from the previous binary join, but we have no other arrangement that we need to worry about. That's pretty handy. So we've potentially reduced, you're producing the same answers at the end. That's good. We've potentially reduced the amount of data. I don't think I wrote it down before, but it's in the chart. Sorry, it's in that chart before. We have that query here already. Good. So if we look now, query 3, which used to have 4 million something. I think we can find it over here. 4 million blah, 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 now has 3.41, something. Less by, not an incredible amount. Certainly not less by as much as we added in for our line item index and a few of these other indexes. But there are 22 of these TPC-H queries, and potentially across the 22 queries, if we shaved off nearly 1 million records, maybe that's actually a net win. I won't tell you. Actually, I don't think I've done the math for that. I've done some of the math, and we'll see some numbers down at the bottom. All right, so this is sort of handy. What I'm going to show you now is just to sort of sketch, there's this secondary index thing, which you can totally read about. It turns out that secondary indexes, all right, if we look at our data flow graph over here, this big index here is because we're joining line items and orders using the order key, by which orders is already indexed, but by which line items is not currently indexed. And because it's not currently indexed by that thing, we've got to build our own, by the order key. We have to build our own index. We could build an index on line item by order key. This is what I'm describing as sort of secondary indexes. So we have that here if we want to build it. We can create an index on line item by order key. It's a foreign key in there. So let's do that. And let's grab the plan again. This is going to be a relatively minor change. I mean, sorry, this is going to be halfway between what we've just done, which does a little bit of sharing, and where we're going, which is going to be a lot of sharing. All right, well, that's a disaster. Let's see if we can. So the optimized plan now, similar to before, has 3 inputs, none of which have any filters now. All of the filters have been moved down to the end. And what we'll see if we go and build this data flow is that this vanishes. This join stage vanishes, and we have still this join stage down here because what can we do? You know, we don't have that. We don't really have any choice there because obviously we haven't pre-computed line items joined with orders. That's not something we're going to do. But I suppose we should make this materialize view. So let's do drop view query 03, and we'll install the new query number 3 with that new index in place. And this will take a little bit of time to hydrate. But we can see its structure already. It's got some more inputs because we were able to. Oh, that's exciting. Did I? Sorry. I think it hasn't properly gotten all the computation it needs to get done quite yet. This join stage should end up, I think, with some records. We'll see. There we go. Good. So worried me because that's the big reveal for the next step. So we have this join operator, and it's just a join between two things outside the data flow. So these are line items indexed by orders and orders indexed by orders. They get joined, they get filtered a little bit, tweaked a little bit, and the results we have to index because we're joining whatever the results are with customers by customer key. So we need to have that that state index so the join can use it. And then we've got some stuff there at the bottom. And we can go and look I wanted to save the explain plan because I've been saving those. Oh, goodness gracious. That's super grim. All right, but we'll save it. There we go. So we've got that new Materialize view installed. Let's take a moment and just look at the sizes of things now. So a few things to notice. First of all, we have this new foreign key index. That's another 6 million records. So that's a lot. At the same time, we've dropped a little over 3 million records by being able to use that index. So obviously that's not a net win with just this one query in place. But if we had multiple copies of query 3 running, or if the 22 queries had roughly similar properties, that can definitely be a net win across the whole query workload. So this query 3 is now an order of magnitude, like 20x almost lower, which is pretty cool, I think. But we're not done yet. Hold on. So let's drop view query 03. The next thing is a little hard to motivate. I'm hoping that the pictures will make it look awesome, and help you understand what's going on. So we added a foreign key index on line item by order key, and that was handy because we needed line items by order key. But it turns out if we had a little bit more, we could actually reduce the memory footprint a great deal more. And the other thing that we're going to need, it turns out it's buried in here, is orders by customer key. And you might say, well, why do we need orders by customer key? We never join, we join line items with orders and then the result with customer key. And you're absolutely right. We do that because we don't have the ability to join orders directly with customers. We always could have, I suppose, but so let's build each of these indexes. What this is going to do is one of the things that I think is really cool in Materialize, really cool in differential data flow, which is a join strategy that is not a sequence of these binary joins. It's going to create a very different data flow graph that I'll walk you through. And the different data flow graph is going to have apparently a number of arrangements quadratic in the inputs. And this would be prohibitive if we actually built private arrangements, right? If we actually built an arrangement the way a traditional data flow system would, private to each of the operators, the amount of memory would just explode. We'd be mental to do this. We're not going to do it. We're not going to do it that way, at least. We're going to share these arrangements, and that's going to result in substantially smaller memory footprint because we use almost no novel arrangements. So let's do an explain plan. I suppose I can just do this over here. Explain. And again, super hard to read. So it's very similar. The main thing that's different, I'm just going to redo this so that it's properly formatted. These arrangements still get brought in. The main thing that's different here, if you look at the join, is the implementation is different. Let's steal this and I'll compare it to the others. Though basically that line is the only thing that really matters. Optimized plans. So, all of the other folks so far have had essentially this same implementation plan, which is a differential. Well, it's a linear join. So it's a bunch of binary joins in sequence, folding in one new relation at a time. It's a totally reasonable way to do joins. What we're going to be doing here instead is this thing called delta queries. And one way to read this is that for each of the inputs, 0, 1, and 2, we're going to build an independent data flow that says how to react to changes in each of those. In the previous plans, the previous data flow graphs that we saw, we built one data flow graph that was able to respond to 3 streams of changes all in the same data flow graph. This is going to be 3 separate data flow fragments that are totally unrelated. They're going to have no connection to each other. And then we're just going to merge all the results together at the end. And it's going to turn out that we're going to, in each of these, use only pre-existing arrangements. So this whole thing will be stateless. It will have no additional state added. So let's grab that materialized view and turn this on and see what it looks like. Ta-da! All right, let's go back and look at our little graph viewer thing, and we'll go down. We'll look here, and all right. So remember how I mentioned that timely data flow graphs, timely data flows, some system Materialize uses, they're hierarchical in nature. So we have, although it's annoying to read, all of our input data going into this region. And we zoom back out. The region, if we look at it, what does it have? Well, it's got a bunch of stuff. Mostly it's got this delta query going on. This is our join. We've also got some reduction that happens outside. You can see here these are these numbers that we had before, handy reductions. But we've got our delta query scope down here. Let's go look and see what's in that. Oof, a little bit of a tangle here. But what we're seeing, if we're presented slightly differently, are 3 different regions, each corresponding to the different independent paths that changes will go through. So there'll be one of these for line items. Changes to line items will come in. They'll probably be joined first with orders and then with customers. Changes to customers come in. They'll be joined first with orders, then with line items. And if changes to orders come in, they'll be joined, don't know, either line items or customers first. It could be either one. I'm not sure which one we pick. But we can explore each of these data flows. Here's this one. I mean, I don't actually know which one this corresponds to, unfortunately. But, we repeatedly do sort of lookups in other relations, various filterings that might produce errors and stuff like that, and then produce some outputs. And the same is true in each of these data flows. But notice there's no red operators. So all of these are reusing existing arrangements, which means that, all told, we go back up a few levels here. This delta query has no arranged state that it maintains, so nothing that it needs to keep as the computation runs. It's going to be borrowing essentially some state, but yeah, it's stateless. So the only state is actually these two operators down here, which hopefully we'll see if we run back here and run our little selectee query. All right. So just again to reinforce some things here, these numbers, we've got even more indexes built on line item. They're just even larger now. So there's 5 copies of them because there are 5 total keys. There's a primary key and 4 foreign keys in line items. We've indexed them each way, even though we don't need each way for query 3. Across the whole spectrum of the TPC-H queries, various of them are useful in different queries. We've got a few different indexes for each of the other relations. So orders, for example, it has orders primary key, so by O key, as well as by customer key, because we happen to know that that's a foreign key that's in there. The part supplier relation is going to have by its primary key, but also by its supplier key and part key. And you can sort of see that various other things show up down here. Here's our query. We're now down by another roughly factor of 5, I think, from what we were at before, to being just the size of the aggregated results. So if you might recall, if we do a select count star from query 03, if you take this number and you double it, you should get that number. And the reason is that Materialize for reductions is going to track both an accumulated sort of an arrangement of the input to the reduction and an arrangement of the output of the reduction. It's just how it works. But pretty tiny at this point. And you can sort of imagine how query 8, which is, let's find it. Query 8, look at this. This has an 8-way join in it, right? So let's go and install query 8. It's going to take some amount of time to get up and running, but once it does, we'll see that it takes basically no state at all. Trying to reload the set of data flows while you're also doing compute at the same time is just this data flow information is all served up by Materialize. It's all relations that the Materialize maintains. Okay, these graph drawings get a bit complicated, a bit grim when you have lots and lots of inputs, but we have roughly 8 different inputs here. But if you look, you can see there's a delta query data flow in there. We zoom in on that. There are 8 delta paths. We can just see the 8 delta paths here actually expandably out. They're all very similar to what we saw before, just a bit deeper. And all of them have no state whatsoever, right? So let's confirm that actually. Let's check and see how much state does query 08 take. You have to look quite a ways actually. There it is, nearly at the bottom. There's 6 records in there. And that's because, I think, if we select star from query 08, yeah, there's really basically not very much we're keeping. I'm not sure why it's 6, to be totally honest. Looks like it could have been 4. But that's what we've got. So you can sort of see, we could go and fire up a lot of these queries and start to see how much memory each of them take. Fortunately, I've already done this for us. It's just a lot of copying and pasting otherwise. It's sort of down towards the bottom down here. There's a big table. Soup. Lots of great stuff to read. Pictures that I drew that I'm happy to have drawn, but even happier if you go and take a look at. And here's a nice visual presentation of what these delta queries look like. Multiple different data flows, each going up independently and getting union together. Yeah, pretty exciting. Late materialization is a cool thing that I'll sort of riff on a little bit once we look at some of the data. It's not a thing that exists in Materialize yet, but you can sort of rewrite your query to make it happen. All right, here's some data. These are a number of records that need to be maintained in addition to whatever indexes are installed at the moment. So, so we've got 22 of these things. Query 20, I should caveat right now. I'm not looking at the moment Materialize this. It has a doubly nested correlated subquery in it, and it's just we don't decorrelate it very well. You can manually decorrelate it, but everything else ran just fine. So I thought I'd just mark it as like, yeah, it's not running in stated form. And generally speaking, I think there's a few exceptions to this, but if you look, baseline numbers, in the millions for a lot of these. Not, some of them, queries 1 and 6, for example, don't have joins in them. They just accumulate. That's fine. But for a lot of these, they got millions of thingies in them with primary indexes. I'm not sure what that shouldn't go up, but it does for some reason. Some of them, they go down. That's query 3. Some of them, they don't really change. It's basically identical, off by 10, which is probably just noise. Some of them go down by a fair bit, 20 million to 12 million. Like, we've definitely cut out a lot of private arranged state there. But as soon as we turn on the secondary indexes, most of these plummet dramatically. So that 12 million goes down to 618. Right, so whatever query 9 is, let's check and see. It's really close to query 8. So here's query 9. It's, I don't know, some six-way join as, well, six-way join. I'm not sure why it's as 20 million-ish as it is. But ends up just being 618 once you've turned on each of these indexes. So across all of these queries, like those 5 copies we had of line item, which is 30 million records, that's mostly accounted for here just by turning them on, and if you need to run query 9 at all. There's some other queries that are not as dramatic, so let me call out a few. Query 13, if you look at it, just has a bunch of state. I'm not too sure that there's anything clever we can do for query 13. Let me refresh myself on what that is. Here's query 13. That was quick. So query 13 is this dealie here. And my recollection is that this is something where we're going to need to, in the course of, essentially we're trying to count the number of customers who have left comments that aren't special requests. And we end up, I think, kind of needing to keep track of some per customer state, and there just happen to be a whole bunch of customers. And just sort of adds up. And we could probably be a bit clever here, but it felt like the cleverness was limited. Like, we cut like a factor of 2 off of this by restructuring the query, maybe more. I haven't looked at it too hard. Another one though that I just wanted to call out because it's sort of cool is query 18. Query 18 is, it's a bit wordy when you look at it. It's this thing here. So, it's a 3-way join. That doesn't seem so bad, but it has a correlated subquery down here. So we want to keep only those order keys that have the property that summed across all line items, that order has a total of at least 300 quantity. And this is a correlated subquery. These are potentially annoying, especially like in full generality. They can be pretty annoying, so you have to be careful planning it. And it turns out we don't plan it perfectly. Essentially, we work really hard to make sure that this query doesn't get executed for order keys that don't appear essentially in orders. Right, so we could, for example, go and just say, hey, for line items, tell me about all the order keys, in orders or not, I don't care, that have a sum of quantity greater than 300. And you can do that, and I did that, actually. So I wrote a different take on the same query, which I'll just install, and a different version of the query 18. Let's call it query 18b. That instead of having that in query up there, it just takes query 18 helper and does a join with it. Yeah. So this is just going to essentially do a semi-join. It's going to restrict ourselves down to those order keys that happen to have this property. But we've given much clearer hint about how we should do this. We should separately go and just figure out those order keys. And then it's just big multi-way join. So let's turn that on. And we're going to be able to compare how much memory does this version of the query require with how much showed up in our records over here, 11 million here. So let's sort of see how it runs. It's still a non-trivial query because this view up here, that's one of the inputs to this join. If we don't have that pre-computed, pre-indexed in any way, so we're going to have to do a fair bit of awkward join planning down there. But we can look and see what happens. So here is our this fragment here is where we are going and essentially doing that first bit of view. We're saying, oh geez, group everything by order keys. Take line items, pull out the distinct order keys. There are 1.5 million of them. Figure out what the quantities are, track those, and keep only those folks with a certain amount. Then we go down to a join. It turns out, just through dumb luck really, that we can enable a delta query down here. We didn't have a pre-existing arrangement for this view that came in, so we knew we were gonna have to build one. Like no matter what, even if we did a boring join, we're gonna have to build an arrangement by some key. And it turns out once we do that, then the delta queries come online because we only ever need this data arranged by that key, right? The only way that query 18 helper ever gets used is by order key. There's no foreign keys in it, so we're good to go. This is stateless. And the only state we actually track are these numbers up here, really, and 57 down here. Turns out that it's an incredibly small number of people who actually satisfy that constraint. Who knew? And everything else is essentially tiny. So if we go back and we look and say how many records are we using in 18B, it's now about 3 million. Right, so it's those 1.5 millions twice, and that's 3 million down from 11 million. So, a little bit of query restructuring, paying attention, it would have been hard to guess ahead of time, but by finessing how we end up doing the joins, we can reduce the memory requirements potentially substantially on a query-by-query basis, basically trying to make them look as much as possible as joins between things that have indexes built for them automatically ahead of time, let's say. There's some additional cool stuff we'd love to be able to do with just get this out of my system, with these sorts of queries. In particular, like when we're doing these counts, we know even at this moment that we only want to keep those people greater than 300. I'd love for this number here to be 57. That would be another factor of 2 reduction essentially in the state, though it's a little tricky to push that filter up into there because the filter could error, and if the filter errors, we don't have a good way to record that in those red bubbles are tracking like legit data. Alas. All right. Just some final comments. This late materialization thing. So what's this about? If we hop over here, you might recall that line item has 6 million records in it. And that's also true for each of the foreign keys. There are 4 of them here. They also have 6 million records in them. And actually, we're not going to change that. We can't have fewer than 6 million, as far as I'm aware. But the thing that's a bit gross is that each of these arrangements are actually keeping the whole line item row, right? So they're keeping all of the data associated with each of the line item records, as opposed to potentially a smaller amount. And in a real database, typically in your secondary indexes, you have less. You have often, for example, for each record, if we're keeping track of the part key one, for example, you'd have part key and also whatever the primary key is for line item. I forget what that is, to be honest. So you just have those 2 fields, right? You have part key and the primary key. And if you need to get the rest of the row, you can always join again with the primary index, right? So you keep your data around by some primary key. Hopefully you have a primary key. Keep your data around by a primary key. And all of your secondary indexes, you can just thin down to the foreign key in question and the primary key, and that just makes them much more narrow. This is a great thing. We want to do this in Materialize. It's going to take a little bit of time because it's some reasoning that we have to do. It's not something that you can see automatically just looking at these data flows, right? So it's hard to say, like, here, is it legitimate for me to go and swap around a few things? But what we can do, which I think is sort of cool, is you can do a SQL to SQL rewrite, essentially, that says, let me make some new views, right? So let me take my line item, I guess what we're doing here is line item foreign key. Sorry, what was I saying? Line item is foreign key by order key. And we're going to make 2 new views on that. We're going to select out from it the order key and the line number. This is what constitutes the primary key for line item. And we'll build 2 indexes on this. One by order key and line number. That's the primary key for line item. And one just by order key. That's one of the foreign keys in line item. So now we have something that if we needed to, instead of maintaining all of line item indexed by order key, we can just maintain this line item FK order key indexed by order key, and then return back to line item if we needed to. Same sort of thing we're doing down below with orders. It's got this customer key in it. We don't need to have all of orders reindexed by customer key. We can restrict it down using a view to just the order key and the customer key and index that 2 ways. And now what we can do, this is great data. Like, we've got all the indexes we might possibly want, as long as we talk about relationships between orders FK cust key and line item FK order key. And we're just going to rewrite here query 3. It's a bit wordier. You might remember query 3 before. It's definitely a bit wordier. Has very similar structure. Like, this is all the same, but we add a few new inputs. So we add these secondary indexes as inputs. Of course, they're derived from line item and orders, so like they're not really independent inputs. But we can plan them differently based on how they get used. And what we end up doing is writing the equijoin constraints. If you remember, there are moments where we equated the customer key and the order key. We're going to connect those to the, we're going to connect things in here by way of these narrow collections. So those are the things that we're going to go and equate. So these have indexes built ahead of time. That's great. And delta queries will fire up at this point and start to run. We'll also connect the narrow and the wide collections, right? So LOK, OCK, back to their collections that they relate to. And in the same way that in query 18, if you remember, like we had that one collection of things that had counts of at least 300. And since we only ever used it one way, we only needed that one arrangement, and delta queries still worked out. And same sort of thing here. We're only going to need line items and orders indexed one way by their primary key, and delta queries will still work out. And we throw in whatever additional constraints we have here. And this is now a query that will be great. It will plan as a delta query, and we will only have one fat representation of line items and orders and customers, in addition to 2 narrow, so just 2-column relations, indexes, to help us turn on the delta queries. So we've reduced, we haven't changed the total number of records, but we've reduced the width of many of the records in these things. And as you can see, this is something that you could do pretty automatically. There's not a lot of thinking that goes into, it's pretty mechanical, I suppose I should say. And either we'll figure out how to do this for you, or make it somehow very easy to do. But it's relatively natural transformation. And it's cool that in Materialize it fires up this new query plans, these delta queries, while further reducing the actual amount of index state you need to keep live in memory. All right, and that's all I really wanted to get through. There's a bunch of really cool stuff to talk about, I think, but I'm just going to leave you with that. All this data to look at and just admire. I don't know. It's like, that these things get. I was honestly surprised that things got as small as this, but it's super cool that they do. If you want to try it out, there's a link at the bottom. Go to materialize.com /download, for example, to download things, or /blog to read things like this there, or just check out the site in various other ways. But that's all I have for you. Hope this was interesting, and I'll try to do more of these as we roll out more content. Cheers.